Episode 1. In the beginning, the Solar Nebula, 4.6 billion years ago. There was no Earth. There was no Sun. There was no solar systems as we know it. In the spiral arm of a galaxy we would later call the Milky Way, there was only a vast cloud of gas, dust, drifting through the darkness of space. This cloud, what astronomers call a molecular cloud or stellar nursery, was cold and dark and mostly empty, but it contained within it the seeds of everything that would come after: every planet, every moon, every asteroid and comet, every living thing that would ever exist on Earth. All of it was there, waiting in that cloud. To understand how our planet came to be, we must begin here, in the primordial darkness, and watch as gravity and chance and the laws of physics conspired to create something extraordinary. The cloud was enormous, perhaps 10 light years across, containing enough material to build thousands of stars and their attendant planets. It consisted primarily of hydrogen and helium, the simplest and most abundant elements in the universe. Created in the Big Bang itself 13.8 billion years earlier, but mixed into that hydrogen and helium were heavier items: carbon and oxygen, nitrogen and iron, silicon and magnesium, all forged in the nuclear furnaces of earlier generations of stars and scattered into space when those stars died in spectacular explosions that we call supernovae. And this is one of the most profound truths of cosmology. We are of recycled stardust. Every atom heavier than hydrogen in your body was created inside a star that lived and died before our sun was born. You are quite literally the sun, the child of an ancient suns, inheritors of their nuclear legacy. For perhaps millions of years, this cloud drifted peacefully through space, slowly rotating, imperceptibly contracting under its own gravity. It might have remained that way indefinitely, or dispersed gradually into the void, if not for a trigger. Something happened. As the collapse began, it could not be stopped. The cloud contracted, and as it contracted, it began to spin faster, like an ice skater pulling in their arms during a pirouette. This is the conversation of angular momentum, one of the most fundamental laws of physics, and it would shape everything that followed. As the clouds spun faster and collapsed further, it began to flatten into a disk, thicker at the center, thinner at the edges. Imagine a ball of pizza dough being spun in the air by a skilled chef, spreading out into a wide, flattened circle. The Solar Nebula, as we call this disk, looked something like that, though on a scale that dwarfs human comprehension. It stretched billions of miles across, and at its heart, where most of the material was concentrated, something remarkable was beginning to happen. The center of the collapsing cloud grew denser and denser. Pressure mounted. The temperature rose. The random motions of gas particles bouncing and colliding generated heat. What had been cold and dark began to glow with a dull red light as the temperature climbed into the thousands of degrees. This was the birth of our sun, though it would not truly become a star for some time yet. The proto-sun, as we call this infant star, continued to grow, accumulating more and more material from the surrounding disk. Gravity pulled gas and dust inward, and the infalling material released tremendous energy. As it crashed into the growing stellar core, the temperature and pressure at the center climbed higher and higher. 10,000 degrees, 100,000 degrees, 1,000,000 degrees, 10 million degrees, and then, after perhaps 100,000 years of collapse, something miraculous happened. Deep in the core of the proto-sun, where the temperature had reached 15 million degrees and the pressure was unimaginable, the hydrogen atoms were forced so close together that they began to fuse, combining to form helium and release enormous amounts of energy in the process. Nuclear fusion began. The sun had ignited. A new star was born. The light from this new star flooded outward, illuminating the disk of gas and dust that still surrounded it. For the first time in 4.6 billion years, counting backwards from today, there was light where our Earth would one day orbit. But there was no Earth yet, no planets at all, only the disk, the remnant of the original cloud, now heated by the infant sun, glowing with its own infrared light. This disk, the Solar Nebula, would be the birthplace of all the planets. It was dynamic, chaotic place, nothing like the orderly solar system we know today. Temperature varied wildly depending on the distance from the sun. Close to the sun, where our planet Mercury would eventually form, the disk was scorchingly hot enough to vaporize rock. Further out, where Earth's orbit would one day be, temperature were cooler, but still far above the boiling point of water. Beyond that, in the regions where the gas giants would form, it was cold enough for water to freeze into ice. In the outermost reaches, it was cold enough for even gases like methane and ammonia to condense into frozen solids. The disk was also turbulent, stirred by convection currents and magnetic fields, by the push of radiation from the sun and the complex gravitational interactions of its own swirling material. It was a maelstrom, a whirlpool of matter into constant motion. But within that chaos, order began to emerge. The tiny grains of dust in the disk, each smaller than a mote you might see floating in a sunbeam, began to stick together. When they collided, static electricity helped, and van der Waals forces, the same weak molecular attractions that let geckos walk up walls. Grain by grain, the particles agglomerated, building up into larger and larger clumps. The process, called accretion, started slowly. Two dust grains became one slightly larger grain. That grain collided with another and became larger still. Over thousands of years, the grains grew into pebbles, the pebbles into rocks, the rocks into boulders, and the boulders into objects miles across, which we can call planetesimals. Planetesimals were the building blocks of planets, ranging in size from few miles to hundreds of miles in diameter. They were solid, irregularly shaped bodies, the first substantial objects to condense out of the nebular disk. close to the sun, where temperatures were high. Only materials with high melting points could remain solid. Metals like iron and nickel, rocky minerals like silicates, everything else, the lighter elements and compounds remained as gas and was either incorporated into the sun or pushed outwards by the solar wind. This is why the inner planets, Mercury, Venus, Earth, and Mars, are small and rocky, made primarily of metal and stone. Further out beyond what we can call the frost line, temperatures were low enough for the water to freeze into ice, and ice is far more abundant in the universe than rock or metal. Here, planetesimals could grow much larger, incorporating not just rock and metal, but vast quantities of water ice, and eventually capturing the surrounding hydrogen and helium gas to become the giant planets Jupiter, Saturn, Uranus, and Neptune. But we're getting ahead of ourselves. Let us return to the inner solar system, to the region where Earth would form, and watch as planetesimals collided and merged. The early solar system was a shooting gallery. Planetesimals orbited the Sun in intersecting paths, and collisions were inevitable and frequent. When two planetesimals collided, the result depended on the speed and angle of impact. A gentle, slow collision might result in the two objects sticking together. Their combined gravity holding them in a new, larger hole. A faster, more violent collision might shatter both objects into fragments, sending debris flying in all directions, some of which would later reaccumulate, some of which would remain as smaller asteroids. Over time, through countless collisions, certain planetesimals grew larger than their neighbors, and the size mattered. The larger an object became, the stronger its gravitational pull, and the more effective it could attract and capture broken objects. The big got bigger. Gravity is a positive feedback loop, a runaway process that concentrates matter into even larger accumulations. These growing bodies, too large to be collided, too large to be called planetesimals, but not yet true planets, are known as planetary embryos or protoplanets. They ranged in size from moon-sized to Mars-sized, and they dominated their orbital zones, sweeping up smaller objects like cosmic vacuum cleaners in the region where Earth would form about 93 million miles from the Sun. As Several of these planetary embryos competed for dominance. Perhaps there were a dozen of them, each growing, each pulling in material, each occasionally colliding with rivals in spectacular impacts that would have briefly illuminated the young solar system with flashes brighter than the sun itself. Computer simulations of this process suggest computer simulations of this process suggest that it took between 10 and 100 million years for these embryos to collide and merge into the four inner planets that we know today. 10 to 100 million years. That seems like an impossible long time, but in the context of Earth's 4.6 billion year history, it is just the opening scene, the first few percent of the story. The collisions between planetary embryos were not gentle. When two Mars-sized objects collide at tens of thousands of miles per hour, the energy released was beyond comprehension. The surface of both bodies would have instantly vaporized. Shockwaves would have propagated through their interiors. Molten rock would have blasted into space. Some collisions would have destroyed both objects, scattering their remains. Others would have resulted in a merger, two becoming one, the combined mass settling into a new, larger molten sphere. This was the violence of planetary formation. The Earth was not gently assembled grain by grain. It was forged in impacts of unimaginable energy, built up layer by layer through collisions that would have sterilized any life, had life existed. The young Earth in these early stages barely resembled the planet we know. It was molten, at least at the surface, a ball of liquid rock, glowing red hot from the heat of the accretion. There was no solid surface, no oceans, no atmosphere as we would recognize it, just a magma ocean, hundreds of miles deep, convecting and roiling, radiating heat into space as a dull red glow. As the material continued to rain down from the surrounding nebular disk and from the collisions with other planetesimals, the Earth continued to grow, and with each impact, more energy was added to the system, keeping the surface molten, preventing any crust from forming. But even in this molten state, the differentiation was occurring. Gravity was sorting the materials of which the Earth was made. The heavy elements, primarily iron and nickel, sank toward the center, while lighter silicate rocks floated towards the surface. This process called planetary differentiation created the layered structure Earth retains to this day. A dense iron core surrounded by a rocky mantle and a thin crust. The sinking of iron to form the Earth's core was itself a source of tremendous heat. The gravitational potential energy was converted into thermal energy, further heating the young planet's interior. This heat, combined with the heat from radioactive decay of elements like uranium and thorium, would keep Earth's interior molten for billions of years to come, driving plate tectonics and volcanism, reshaping the surface again and again. Around the time, perhaps 50 million years after the Solar Nebula first began to collapse, the young sun entered a new phase. The Tauri stars, as we call stars at this stage of development, are notoriously active and violent. The sun would have been far more luminous and active than it is today, emitting powerful stellar winds and intense bursts of radiation. These winds began to clear the Solar Nebula, blowing away the remaining gas and dust that had not yet been incorporated into the sun or the planets. This was a critical moment. Once the nebular disk was cleared, the raw material for a planet building was gone. Whatever planets had formed by this point would be the final result. Though they might continue to grow through collisions with leftover planetesimals and embryos for some time to come. In the inner solar system, 4 rocky planets had emerged. Mercury, closest to the Sun, small and dense, stripped of any volatile materials by the Sun's fierce heat. Venus, the Earth's near twin in size, though its story would diverge dramatically from ours. The Earth itself, the largest of the rocky planets, and Mars, smaller, farther out, cold, and dry even in its youth. But the process was not finished. The early solar system was still filled with debris, uncaptured planetesimals and embryos that crossed the orbits of the newly formed planets. And one of these objects, perhaps the size of Mars, was on a collision course with Earth. We will meet that object, which scientists have named Theia, in the next episode. The collision between Earth and Theia would be the most significant event in our planet's early history, reshaping Earth and creating the Moon in a single catastrophic impact. It would be a collision so violent that it would melt the entire planet, so energetic that it would nearly tear Earth apart. And yet, from that destruction, something beautiful would emerge. But stars collapse under its own gravity to form a new star and a disk of material around it. We have watched as the disk cooled and condensed, and dust grains stuck together to form pebbles to form boulders to form planetesimals, and planetesimals to form planets through countless violent collisions. We have seen Earth emerge from this chaos, a molten ball of rock and metal differentiated into layers, glowing with the heat of its formation. We have seen the Solar Nebula dispersed by the young sun's winds, leaving behind the architecture of the solar system we know today. All of this happened in the first 100 million years, a period geologists call the Hadean Eon, after Hades, the ancient Greek underworld. It was well named. The early Earth was indeed a hell, an inferno of molten rock and catastrophic impacts, utterly inhospitable to life as we know it. And yet, this hell was necessary. Without the heat of accretion and differentiation, the Earth's interior wouldn't have remained molten, and without a molten interior, there would not be magnetic field to shield us from solar radiation. No plate tectonics to recycle nutrients and regulate climate. Without the violent collision of the late stages of accretion, we would not have the moon. And without the moon, Earth's rotation would be unstable, leading to wild swings in age and climate that would make complex life difficult or impossible. Even in destruction, there was creation. Even in chaos, the seed of order. The universe tends toward entropy, toward disorder, and yet here, in this small corner of space, order emerged, structure formed, a planet was born. That planet was not yet the Earth we know. It had a long journey ahead, through bombardment and cooling, through the formation of oceans and atmosphere, through the emergence of life and the slow transformation of a barren rock into a living world. But the foundation had been laid, the stage had been set. In the darkness of space, orbiting a young yellow star, in an ordinary spiral galaxy, a pale dot was beginning its long story. A story that would include wonders and terrors, triumphs and tragedies, extinctions and explosions of diversity. A story that would eventually include us, creatures capable of looking back and underestimating our own origins. Children of the stars contemplating the cosmic accident that brought us into being. The journey has begun. The Earth is taking shape, and ahead lies 4.5 billion years of transformation, of ceaseless change of a planet learning